All right, well, welcome everybody to the Economics of Electrifying Buildings for our weekly Wednesday webinar series. Real quick, do you want to see greener and better homes for all? Tired of registering for all of our courses and want to get discounts on all sorts of educations and green building certifications? Go to our website, greenhomeinstitute.org, become a member, and check out all those benefits today. This particular course here is approved for 1 hour in continuing education units, GBCI, AIBD, NARI Green, Certified Green Home Professional, and BPI NonWholeHouse units, as well as American Institute of Architects Health, Welfare, and Safety, which may make it applicable to your state-based design or contractor license. This course is brought to you by the nonprofit, the GreenHome Institute, and today I will be your moderator. My name is Brett Little. And overall, what we're going to be talking about today is just highlighting how the hashtag Electrify Everything movement is well underway, and really asking the question, is it financially economical to start to electrify all of our homes and all of our buildings? Before we jump into that, a quick word from our sponsor, Build Equinox, featuring the new CERV2 smart ventilation system. With a standard ERV-HRV, you get constant low air flow rate with no relation to actual indoor air quality or occupancy. For the first 3 days when the home is occupied, the air quality is poor. The ERV just can't keep up. When the occupants leave on vacation, the ERV keeps ventilating and wasting energy. Since the CERV actually monitors air quality, it ventilates only when it needs to. Compared to an ERV, the CERV can ventilate up to 300 CFM, quickly purging pollutants from the home. When no ventilation is needed, the CERV can recirculate and unify the home, providing some additional heating, cooling, dehumidification in an energy-efficient manner. The CERV does this by monitoring both CO2 and volatile organic compounds levels to determine when ventilation is necessary. Many gases are undetectable to the human nose, yet can cause significant impairment to health, cognition, and sleep quality. Even though you can't smell them, the CERV can. Monitor your indoor air quality, change your set points, and configure the CERV to best suit your home and lifestyle with ease. Now, instead of an ERV exchange core, the CERV uses a high-efficiency heat pump to exchange energy between incoming supply and outgoing exhausted air. Now, what does this mean? Conditioned, comfortable air unifies the home instead of dragging exterior rooms away from comfort. The CERV's filter access panel allows the homeowner to easily access and inspect and replace both indoor and outdoor air filters. The CERV accepts the standard 10 by 20 size with your client's choice of filtration. MERV 13 comes standard in the unit. One bonus is the CERV is manufactured right in Urbana, Illinois, 100% American-made, in a facility powered by 100% solar power. Now, the CERV can work with a heat pump water heater, such as the Rheem Prestige, to boost it. It can work with a Mitsubishi mini split to distribute air around the home or multifamily unit. And finally, it can work with its new GeoBoost add-on feature to sync with GeoComfort geothermal systems. Go to buildequinox.com today to learn more. All right, well, I'm excited to introduce our speaker, Mike Henshin. He's manager with RMI's electricity practice. He focuses on utility business models and innovation and manages RMI's ongoing work supporting a resilient, affordable, clean electricity system in Puerto Rico. Mike has contributed to RMI's Reimagining the Utility Work, an assessment of lessons learned in utility pilot and demonstration programs at the distribution edge, and upcoming paper on electrification of building heating. He has also worked with leading utilities to build and expand innovative business models supporting the transition to an affordable, reliable, low-carbon energy system. Mike is interested in developing solutions for clean energy futures that benefit both customers and utilities and mitigate the impact of climate change. So with that, welcome, Mike, and take it away.
Okay, thank you, Brett. All right, we will be talking today about the economics of electrifying buildings. So let's jump right into it. And please, as Brett mentioned, feel free to lob your questions his way as we go. So first, we are Rocky Mountain Institute. We're a nonprofit focused on the global energy transformation, and climate change and decarbonization is a big part of our work. So to get us started here, as a fact base, we know that fuels are burned in buildings, homes and businesses, and that accounts for nearly 10% of all U.S. greenhouse gas emissions. So in the donut chart here, we see the entirety of economy-wide carbon emissions in the U.S. according to the EPA in 2015. So you see the little orange slice in the bottom right is fuels that are actually burned on site in buildings, and that's almost as much as cars, and about a third as much as the entire electricity system. And where does this come from? Primarily it's space heating. Water heating, cooking, and other smaller end uses are significant as well. But space heating is really the dominant, and water heating the number two. And the residential side of this is slightly larger than the commercial side, but they're both comparable in scale. So we said we wanted to investigate this opportunity, this hypothesis, that efficient buildings could power all of these end uses with low carbon electricity and eliminate fossil fuel use in buildings and their emissions and other issues associated with indoor air quality and safety that go along with burning fuels in buildings. And secondly, that these end uses can be interactive with the electric grid and can balance wind and solar power, which are variable resources. So, we launched this report with the big question of how do we decarbonize buildings, and should we pursue this path? Should we, as a nation or as states or cities, be switching people and businesses from natural gas, from oil, from propane to electricity? Does that actually make sense? We had heard a couple assertions that gas is always cheaper, or that it's better to burn gas at the point of use rather than to burn it at a power plant and transmit it over the wires. So we wanted to investigate that. So the scope of this report asks a couple main questions. Does electrification reduce or increase carbon emissions today with the grid we have, the electric system we have today? And does it reduce or increase long-term cost? So, we'll talk about the mix of what we looked at in a moment, but it was limited to single-family homes with ducted heating and air conditioning. We did not include multifamily or commercial buildings, other heating systems without ducting, ground source heat pumps, or renewable gas. But we did look across these variables here. So geography, 4 cities, Chicago, Oakland, Houston, Providence. These were selected to give a mix of climate types and of electricity pricing and gas pricing and how customers are charged for those things. We looked at new construction and retrofit. The new construction homes represent a much higher degree of efficiency than the retrofit homes, which would be more of an average or medium performing building. We did investigate a variety of electricity rates and try to say how could we, what are the creative tactics we could use to optimize for those rates? Can we preheat the water when electricity is cheap, for instance? We considered whether a customer was replacing only a furnace or whether they could get kind of a 2-for-1 benefit and say that they're both their air conditioner and furnace were at the end of life and would be replacing both with one air source heat pump. And then we looked at a few different fuels: electricity, gas, propane, and oil. So let's dive in a little more. Okay, last point on methodology. We did use Energy Plus as our modeling software for the carbon emissions associated with electricity. We used this marginal emissions data, and what that is on a 5-minute increment for the entire year in that city, what is the power plant that's turning up or down just a little bit to accommodate more or less electricity. And so it's very, very granular in terms of which emissions, which power sources are actually responsible for meeting additional load. And we did use heat pumps that meet the cold climate certification. Okay. I'm going to dive into the highlights here, and then we'll dive into some city-by-city results and talk about how the numbers shook out. So, the first point is it cost effective? And we found kind of a mix, but we found the answer is yes in several situations. So pretty much all of the new construction situations came out as cost effective under our analysis. There's a couple of reasons for this. One is that you get a bit of a 2-for-1 benefit. You're installing one air source heat pump instead of both an air conditioner and a furnace. And you save a little bit on natural gas infrastructure in the building, and you could save a lot on avoiding the underground gas infrastructure that serves the home itself. Also, the new construction buildings are much more efficient and are a better match for air source heat pumps, including in the colder climates, than the less efficient buildings are. The oil and propane, we only looked at those scenarios in New England because we know oil in particular is common there, but it is relatively cost effective to electrify those customers under our analysis, considering they do not have gas service already, so natural gas is not an option for them. And then some of the existing natural gas customers, the hardest customers to convert from a cost point of view are those who already are served by natural gas. But in some situations, as I mentioned, if the air conditioner and furnace were both at end of life and they could swap them out at the same time for one air source heat pump, they could come out ahead in that scenario. But it becomes harder to do it on a proactive basis if they wouldn't otherwise be replacing those devices. We'll get into the electricity rates. You get some value out of optimizing for time of use electricity rates, but it's not usually enough by itself to change the outcome. And then in terms of carbon, unless you have a really coal-dominated grid, it's definitely reducing emissions to go to efficient heat pump electrification today. So we'll talk about why Chicago was different when we get to the Chicago results. But now I'm going to dive in and talk about, city by city, what the specific outcomes were. Okay, so here we see Oakland. So these slides will all have the same format. So what we're looking at here, the green is all the electricity scenarios and the blue is natural gas. And we're just comparing on price. And the price is basically over the lifetime of over a 15-year assumed lifetime for this equipment, both considering the upfront cost of the equipment and installation and the energy cost over 15 years. So over that time frame, we see, in new construction, as I mentioned, the green, the electricity is looking like a lower cost alternative. And you can see that largely you're getting that benefit out of the lighter shaded part of the bar, which is the fixed cost up front. And that's because you're saving. You're basically buying one device instead of two, and installing one device instead of two. And there's some, reduced need for venting and other things associated with the use of gas. In the retrofit scenarios, it's a bit more mixed. By far the cheapest here is this bar that says 16.1. That's the natural gas customer. They otherwise would not be replacing an air conditioner. They have an existing air conditioner. They wouldn't be replacing it. And so all they're doing is swapping out a furnace, and that tends the swapping out a furnace for an air source heat pump rather tends to be a bit more expensive, just on the fixed cost of replacing all that equipment. The other points here that are highlighted below, the different green bars are different electricity rate structures. The top is just the standard. The second one, if we think about California, they're going to put every customer in the state, or just about, on a rate that varies. It's more expensive during the evening peak periods, less expensive at night, or maybe during the middle of the day, given all the solar power in California. And so we said, what happens if we tried to use those cheaper periods to preheat the water, to preheat the home during the winter, or pre-cool the home during the summer. We found a bit of mixed results there. The second line is this default time of use that everyone is going to be on. And in that rate, the customer pays only about 20% more during the peak period. It's not that much more expensive for electricity. So given, you don't really get a lot of value out of pre-cooling your home during the summer or preheating it during the winter. It ends up being more expensive just to add the extra control equipment you need to manage that. But, if we go to this third line that says 3-to-1, that imagines a rate where it's 3 times more expensive in the evening and much cheaper in the middle of the day. In that scenario, you can get some value out of it. The price difference is large enough to make it worthwhile to pre-cool your home in the summer. I think we pre-cooled it down to 67 or 68 degrees when electricity was cheap, and then we didn't have to run the air conditioner during the more expensive times of day. Great. I see a question pop up. I'm actually going to respond to that right now. So why are the numbers for both space conditioning and water? Great. So everything is included here. So we said, the scenario is that the home is electrifying everything. So they're swapping out a gas water heater for an electric heat pump water heater, a gas furnace for an air source heat pump. And we wanted to see the totality of the economic value proposition for that customer. So, the scenario kind of bundles it all together and says what's the entire result. If you have detailed questions about sort of the split, how water heating might be different from space heating, you can feel free to ask those and we can come to those later. All right, I'm going to move through. So the other side of the Oakland analysis was carbon and saying, do we come out ahead or behind? So here we see, the green bars are all shorter. So the California electric grid is already relatively clean. Even if we use this marginal emissions methodology we described, a lot of times that marginal power plant is a natural gas power plant. But even so, even if you assume you're always burning natural gas to power the heat pump, you still come out ahead. And a big part of the reason why is just how heat pumps work. The fact that they have a coefficient of performance of 2 or 3 or even 4 in some conditions, and they are, especially in a mild climate like Oakland here, they're extremely efficient devices and are making very efficient use of that electricity. So you come out ahead in all cases here. And in a place like California or other states that have a high renewable standard already written into law, in California now it'll be 100%. We know that over time, all of the new power plants that are constructed are going to have to be renewable, or at least zero carbon. So we know that by 2045, if the law stands, all these green bars will go to zero. And that's really the promise of this approach. And then the other thing just to recognize is obviously the left side, the new construction, those bars are only about half as long as the retrofit bars. And this is just a recognition that efficiency really matters. And whether it's a new building or an existing building that undergoes an efficiency retrofit, you can really slash both the environmental impact and the energy costs with efficiency. So that continues to be extremely important. Okay, great. So we're going to walk through a couple other scenarios and just see what's the same or what's different when we look to different cities. So this is Houston. So, it's similar in that the main headlines are really similar. New construction, the costs are still lower for the all-electric options, the green options. And in the retrofit, it's more mixed. The lowest cost is still a customer who just sticks with natural gas. But we've tested out a couple other things here. There's, on the electricity rate side, there's something unique offered in Texas. You may know that Texas has a retail electricity market where all customers can shop around for their electricity provider, and they offer all sorts of creative types of electricity rates. So one of them is called free nights that we found, where literally as a customer, you pay $0 for electricity between 9 p.m. and 6 a.m. every day of the year. And to compensate for that, you pay a more expensive price during the day. And so we said, could we take this to the extreme? What could we do with that free electricity? Could we maximize? Could we really severely pre-cool the house during the summer? Could we really preheat the water all year round? And then at 6 a.m. when the price changes, you've got a cold house and a hot water tank, and see how long you can go through the day without using any more electricity. And I would say we found that looking across the entire year, that didn't quite work out as well as we had hoped in terms of saving the customer money. That the issue is that the air conditioning cost in the Houston climate is just so high that you can't make it up. You can't pre-cool the house enough by 6 a.m. to last you through the hot afternoon. And the fact that you're paying more for afternoon electricity makes it a bit worse. So it was an interesting experiment to test, but we found that in this case, trying to pre-cool the house to 6 a.m. to last through the afternoon on a hot Houston day didn't really cut it. All right. I'm going to move through to the carbon side here. I
think there was a quick question. Was the TOU the only electric rate taken into account? Utilities can also have interruptible rates or reduced electric rates for electrical-based heating.
Yes, and I see also about the gas meter fees. So TOU was the only rate we used. So in the California scenario, so one of the things you mentioned is reduced electric rates for electric-based heating. So in the California scenario, yes, we did include that. So that's a state where if you're on all electric heating, then you actually you end up paying a lower rate for electricity. So we did incorporate that into the California scenario. So the electricity customers get that benefit that the natural gas customers don't. That particular rate doesn't apply in Houston or the other states we looked at. We did not look at interruptible rates in this case. And then removed gas meter fees. So yes, absolutely. So every city is different depending on what the gas utility charges. Off the top of my head, I want to say that in Oakland, we looked at PG&E's gas rates, and they did not have a significant gas meter fee. So when we talk about the gas meter fee, how that shows up for the customer is on their gas bill, it might say, $10 per month is just the fixed charge that they pay every month regardless. And as long as you have gas service, even if you hardly use any gas. In the California case, that number is very small, or $0. In the Rhode Island case, which we'll get to shortly, it was over $30 per month fixed charge. So that is very location dependent or utility dependent, and we did include that in the analysis.
And to follow up on that, did you find, and maybe not in those states, but in any other states where maybe you legally couldn't have, you had to have a gas meter?
No, we didn't. In our scenarios, our understanding of these particular utilities is that the customer has the option of discontinuing gas service entirely, so that the customer could do these retrofits to their home, call up the gas utility and say, I want to discontinue gas service, and then zero out that portion of their bill. Now I know in some states there can be requirements that gas especially for new construction, that gas service has to be extended to the home. So for the purpose of our analysis, we made the assumption that a home could be constructed without gas service altogether. Okay. Great. Well, to look at the flip side of Houston on the environmental side or the carbon emissions side, the Houston, the Texas grid is a bit more mixed in generation sources than California's, but still the natural gas is sort of the dominant generator on the margin. So this emissions analysis ends up being compared to burning natural gas for electricity. So it's somewhat similar to California. The green bars for the most part come out a bit ahead, not as big a benefit as California, but it is some reduction immediately, even without more renewable generation. And even in Texas, which does not have an RPS the way that California does, not a significant one, we know that there's a trend towards more wind energy, starting to be a trend toward more solar, and a trend toward retiring coal. So we would anticipate that this would get better. The exception would be this unique case with the flexible heat pump on the free nights rate. We described really aggressively trying to cool the home down at night or heat the water up. Because the electricity was free, our simulation really used a lot of electricity during those hours. And while it didn't cost the customer anything, it did have a larger emissions impact. So we found there's a bit of a perverse incentive there to overuse electricity in this middle case, the third bar, and that kind of comes out to the detriment of the environmental impact. So in this case, we didn't recommend the free nights rate as an actual benefit for the customer. Okay, so here we're going to take a little deviation into how the electricity is used. And so this, through the course of a day, how is electricity used under different scenarios? And the reason we care about this, one reason we care about this, is because the impacts on the electric grid are going to be really important for the success or failure of the electrify everything movement, I would say. So for instance, the naysayers might say that if we're just loading up electric demand at the wrong times of day, we're gonna overload local parts of the grid. We're gonna require new power plant construction. It's gonna be very expensive. So doing this effectively would require managing the timing of when electricity is used. And so we wanted to see how can we actually shift that electricity around. Okay, so here's the Houston example I talked about. The top chart is just the standard. This is in January. It's not very cold in Houston, but there is a heating load. And you can see they're heating a lot in the early morning, in the red there, not as much in the middle of the day, and picking up more in the evening. The water heater usage is kind of random. For some reason, this customer profile is using some in the early morning. But then when we try to optimize for this free electricity at night, you can see we really spike the nighttime use, even for heating. So we're preheating the home, we're preheating the water. And the things I would take away from this in the bottom chart is, one is that, this is the sort of the retrofit scenario. The home's not super tight, not super efficient. And even with preheating the home, as much as we did, you still need to use electricity for heating pretty much right away in the morning. It's reduced some from the top bar, but it's still there. So the preheating benefit is fairly limited, in particular with a home that's not that efficient. In the blue, you can see that we get a better benefit out of the water. We're able to not use any electricity up until almost noon. So we get at least 6 hours of deferred electricity usage for the water tank. So that's a benefit we have there, but the preheating for a poorly efficient home doesn't work that well here. And then to look through another example, so this is really the same thing, but during the cooling season. So this is in July. So first of all, you can see, well, there's a lot more energy use because it's Houston in July, where we have a lot of air conditioning load. But once again, if we really try to pre-cool the home, it's, I think in this case, in this scenario in the chart here on the bottom, we pre-cooled it down to 70 up until 6 a.m. and then changed the set point to 75. And just that 5 degrees of pre-cooling, it gets you a little benefit for an hour or two maybe. But by the time it's really hot in the afternoon, there's no discernible impact. So what we're saying here is that this, at least with this particular rate, trying to pre-cool at 6 a.m. and then have that benefit linger and last in the home until the afternoon on a hot day in Houston, it just doesn't quite cut it. Great. Okay, I see there's a couple other questions. Before I move on, let me see if we can address some of these questions. Okay, so the question here I see about not recommending continuous HVAC versus using a thermostat that only runs at certain times in a passive house. Well, I would clarify that the recommendation here is that, this concept of running continuous HVAC, during one period to preheat or pre-cool, it works pretty well for a water heater. That concept anyway works pretty well for a water heater, and I would absolutely recommend doing that with water heater, because you see here we're getting a big benefit out of that. But the majority of the energy use is for space heating, and it's pretty limited. So I would say that strategy can be beneficial, but is quite limited. And what really matters more, which we'll see on the next chart, is the efficiency of the house, much more so than pre-cooling or preheating the home. So if we just flip forward one slide, we'll compare this to the efficient home, and we just see everything just gets smaller. So this benefit between the top and bottom of deferring some energy usage for a few hours, it might be good in some limited situations. It might be if there's a really cheap energy followed by really expensive energy within a few hours of each other. But efficiency of the home is just much more valuable for the sake of reducing this energy impact. Okay, we're going to move on and talk through the other cities and then a few implications. So these are a bit similar, so I'll just focus on what's different. So really what's different in Providence, Rhode Island is that we considered a couple other fuels, heating oil and propane, and generally found that those are, well, they're more expensive. They're certainly more expensive than natural gas. The propane pricing in New England is quite expensive, so that would be much less advantageous from a cost point of view. Heating oil is slightly more expensive than the heat pump option, even in a somewhat colder climate that Rhode Island represents. So the energy cost associated with heating with oil or propane is just higher, and those customers are going to be more attractive targets for electrification than the natural gas customers. The New England grid and Rhode Island grid is quite clean, actually, cleaner than California's even. So from an emissions standpoint, it's quite clear that the green bar on top, the heat pump, is the winner, and that all the New England states and New York have aggressive carbon reduction goals, and we'd expect that only to continue to improve over time. And then lastly, we looked at Chicago. So, I think the cost numbers shake out pretty similar. New construction is beneficial, retrofit, not as much. But the other interesting thing about Chicago will be the emissions impact. So if we think about where power comes from in Chicago, it's a mix of coal and gas and wind in the region. But the analysis we used was just what's on the margin, and based on the data from the market operator, it actually shows that they're using coal on the margin a lot, meaning that they're actually balancing with coal. This was surprising. It wasn't what we expected, but it's what the system operator's data shows. So if we use that data and assume that it's basically a coal-based impact for new electricity production, it comes out looking poor. for carbon. Now, our expectation is that this is changing rapidly, and coal plants are retiring across the Midwest. And actually, it's not, the long-term view will actually be much better than this. But if we only took the short-term immediate impact view, it would look relatively poor from an emissions point of view for electrifying with a heat pump.